Today we'll start talking about symmetric encryption. The symmetric encryption algorithms that are in use today try to meet two conflicting requirements. The first is to provide computational security against even a well-resourced attacker, and the second is to have manageable key requirements. So in particular, we're looking for ciphers that use a fixed length key, unlike the one-time. And cryptographers use two main tools when building symmetric encryption algorithms: transposition and substitution. Let's talk about transposition first. The definition of transposition is that symbols of plain text are rearranged and reordered in the ciphertext. So for example, anagrams work by transposition. Let's see what happens if we don't have transposition in order to better understand why it is important. So here I have used the Caesar cipher to encrypt a few sentences. So there is no transposition here. And you can see the patterns of the language remain in the ciphertext. For example, the letter combination TH appears frequently in the English language. If you encrypt the first paragraph using the Caesar cipher, the patterns in the language are maintained and can be used to decrypt. The BP letter combination remains and can be a clue for figuring out the shift amount. Other frequent letter combinations in English are ing or ed, st, ch, and words ending in F. So transposition breaks up patterns in the plain text. It disrupts the statistical structure of the plain text. And this can be structure that exists in language, like we saw in the English language, or it can be structure that is dictated by a protocol being used in communication, by headers that are used, file or communication headers, or structure that exists in code, which is very well structured. The transposition would break up that pattern and make it more difficult to successfully attack. Okay, let's talk about substitution next. Substitution means that each symbol of plain text is replaced with a new symbol. And we've already seen examples of substitution. The Caesar cipher and one-time pad both work by substitution only. Substitution obscures the original symbol. So to understand why substitution is important, let's look at an example of what happens if we do not have substitution. If you don't have substitution, then if you know what to expect, for example, a sentence that's written in English, then just getting the set of symbols used, even if they are out of order, might be enough to figure out the original message. So here in this example, I have used transposition only with no substitution. And you can see that although it might take some doing, you could probably take the second line and with no knowledge of the first line, figure out what it says. So substitution obscures the original symbols. But note that a fixed substitution is not enough. As we've seen many times so far, the Caesar cipher, which uses a fixed substitution scheme, is easily broken under a ciphertext-only attack. And that is because the symbols repeated in the plain text are repeated in the ciphertext and give us clues to decrypt the message. So here, this is a fixed substitution scheme I have used to encrypt a popular American nursery rhyme. See if you can figure out what the original plain text, what the nursery rhyme is, even without figuring out, what the substitution scheme is that I've used. Okay, now that we've established the building blocks of symmetric encryption algorithm, let's talk about some actual algorithms. We've already seen examples of symmetric encryption algorithms, the Caesar cipher and the one-time pad. And these are both examples of stream ciphers in which plain text symbols, for example, the characters or the bits, are encrypted one at a time. There's another flavor of symmetric encryption algorithm, and that is the block cipher. And we're going to talk about each of these. Let's start with stream ciphers. A stream cipher is a cipher in which each symbol of plain text, so each bit or byte or character or digit, is encrypted separately. And examples include the Caesar cipher, the Vernum cipher, which we talked about, the one-time pad, and RC4. RC4 is another stream cipher. We will not go into it here, but it is used for encryption in wireless networks. An advantage of stream ciphers is that each bit or byte of the plaintext can be encrypted or decrypted as soon as it's available. So if you have data coming in off a network, for example, you can start decrypting as each new byte of data arrives. So next we'll discuss block ciphers. In a block cipher, groups of symbols are encrypted together as a single block. And examples of block ciphers are AES, DES, and triple DES. The algorithm, the encryption algorithm, does the work on the whole block all at once. And block sizes are fixed. 64-bit, 128-bit, and 256-bit blocks are common sizes. And the encryption must be done on blocks of that size. The first one we'll talk about is DES. It was developed in 1977 for the US government. Since then, standards organizations in both the US and internationally have accepted this, so it is an internationally accepted standard now. It uses 64-bit blocks and 56-bit keys, and it works by substitution and transposition in cycles. So there are 16 cycles of substitution and transposition used in the DES algorithm. In each iteration, substitution takes place, the replacing blocks of bits with some new bits, and permutation takes place, shuffling the bits around. The other thing that takes place in each iteration is a key transformation step, in which bits from the key are mingled in with the bits from the ciphertext. It is repetitive and uses simple arithmetic and Boolean logic operations, making it fast. However, as we've already seen, 56-bit keys are too short. So the key length is really too short for today's computers. However, the algorithm is secure. And so it's not a secure algorithm to use just because the key length is too short for today's computers. And some 56-bit keys have been broken in a matter of days. But the algorithm itself has never been successfully broken. The successful attack has always been through brute force search. The next one we'll talk about is AES, and AES stands for the Advanced Encryption Standard. This one is in widespread use today. It was developed in 1997 in an open call from NIST, the US Standards Organization. It was developed by two Belgian cryptographers with no affiliation to any government entity, and it was intended as a replacement for DES. The algorithm it's based on the Rijndael algorithm, and there are some differences to the Rijndael algorithm, most notably that AES fixes the implementation to be over 128-bit blocks and with 3 options for the key length, either 128-bit keys, 192-bit keys, or 256-bit keys. So we're going to talk a little bit more about AES and the basic Rijndael algorithm. It is a substitution permutation network, and it operates in rounds. Each round consists of a byte substitution step, a step of shifting rows, a step of mixing columns, and then finally a step in which the round key is added in. So a 128-bit round key is needed for each round, right? This algorithm operates in rounds, iterations. You need a new 128-bit round key for each round, and this key is produced from the encryption key using a key expansion algorithm. The algorithm is defined for either 10, 12, or 14 rounds, depending on what size key you are using. Maybe you can have 128, 192, or 256-bit keys. Before the first round takes place, there's an initialization in which the round key is XORed with the bytes of the state. And AES is secure, but there have been weaknesses found in reduced round versions. So if you're looking at, maybe a 6-round or 8-round version of AES, which is not how AES is defined, so that's not the AES standard. But if you do look at these reduced round versions, there have been some weaknesses found in the algorithm. And this is a weakness in the algorithm, so not that keys have been found through brute force search, but that actual weaknesses have been. However, AES, as described as standardized, is still secure. So let's talk about the 4 steps. The intermediate ciphertext produced by each round is called the state and can be represented by a matrix of bytes. So on the left-hand side of the screen, you see a matrix of bytes. That is the state. The first step of each round is substitution. And this is done at the byte level. So byte substitution is done, and it's done using a lookup table, and this is called the AES S box. And this S box is fixed. It's a fixed 8-bit lookup table. The same S box is used for all bytes. The next step is to shift rows. And so in this step of the round, you have your matrix of bytes. The first row of bytes does not shift. The second row is shifted 1 byte to the left. The third row is shifted 2 bytes to the left. And the fourth row is shifted 3 bytes to the left. The third step of each round is the mixed column step. And here, each column is treated as a polynomial and multiplied by a fixed polynomial. This C of x is a fixed polynomial. And again, this is a fixed polynomial that is always used in the mixed column step of a round. The shift rows plus the mixed columns together provides diffusion. The last step is the add round key step. In the add round key step, the bytes of the matrix of the state, the current state, are XORed with the key material, the round key material, and the result is the new state to be fed into the next round. So let's talk about the properties that we want from a strong symmetric cipher. All symmetric encryption algorithms have the same basic structure. The key and plain text are combined in some way to produce the ciphertext. And this means that there is a link between the key and ciphertext and between the plain text and ciphertext. Cryptanalysis, the breaking of ciphers, tries to leverage that link to recover the plain text or key material from the ciphertext. Sometimes this is easy. For example, in the case of the Caesar cipher, the link between the plain text and ciphertext is so strong and clear, the cipher is easily broken. In the case of the one-time pad, it is proven to be impossible to recreate those links without knowledge of the key. But for symmetric encryption algorithms that we use today, the algorithm uses a fixed length key, but is still, hopefully, not easily broken. We want the cryptanalyst to be reduced to using exhaustive search. Claude Shannon in 1949 outlined 2 properties that make for a strong symmetric cipher: diffusion and confusion. Diffusion says that you want diffusion, and diffusion spreads the plain text statistics across the ciphertext. So changing one character of plain text changes several characters of ciphertext. And this is done to disrupt the statistical structure of the plain text. The frequency statistics of letters in plain text are diffused over several characters of ciphertext. As a result, many more examples of ciphertext-plaintext pairs are needed for a successful attack. And we said that this is what happens in the shift rows and mixed columns step of the Reindahl algorithm. Confusion tries to obscure the relationship between plaintext and ciphertext. Stream ciphers depend entirely on confusion. That's not necessarily bad. For example, the one-time pad relies solely on confusion and is perfectly secure. So we know that confusion on its own is sufficient for security. However, practical stream ciphers are weaker than a one-time pad. In particular, the key material is generated deterministically and is reused, and so without the benefit of diffusion may be weaker. So to sum up, we have stream ciphers and block ciphers. Stream ciphers offer low latency. The decryption can happen on that first bit as soon as it arrives. Stream ciphers offer no diffusion. Each bit of plain text is correlated to one bit of the ciphertext, or byte, a byte. But stream ciphers do seek to offer high confusion. On the other hand, block ciphers offer higher latency. You need a whole block in order to start any decryption or encryption. Block ciphers do offer higher diffusion. Each bit of or byte of the plain text is diffused through multiple bits or bytes of the ciphertext, and also high confusion, where the correlation between plain text bits and ciphertext bits, or plain text symbols and ciphertext symbols, is not clear. It's obscured. Okay, we'll stop here.